Okay, hello everyone. Welcome back um, to um, chapter three. So we're going to continue off where um, we ended last time, and we were just talking about uh, pretty much a review of chemical nomenclature, what are compounds, what are molecules, the atomic compounds and molecules. So now we're going to start talking about how do we determine how much of each element is in a compound. How do we know that a chemical compound has this many carbon atoms or has this much percent of carbon, hydrogen, or oxygen? So we're going to delve into that today. Okay, so um, so how do we determine chemical composition? So the way we do it is it's called combustion analysis or composition analysis. So usually we take our sample and we're going to combust it or basically convert it to carbon dioxide and water. So we have our little furnace here, seen figure 1.16. This is used to determine the percent mass of carbon and hydrogen in a compound. So we have oxygen, we have our furnace, we're going to do a combustion reaction. So essentially we're going to blow it up and cause a chemical reaction that releases a lot of heat, and in the form, our sample now is going to be in the form of water and CO2. Okay. So what happens here is water will absorb into a compound or will absorb onto a sample of magnesium phosphate. Of known mass, so you need these chemical absorbers so you can determine like how much water was formed or how much CO2 was formed. So usually we have a known mass of, say, a chemical that can absorb water. And then we can determine the mass of water just by taking the difference between the mass of just this magnesium perchlorate, or we can and we subtract that from the mass of perchlorate with the absorbed water. So a routine procedure in the lab, how to determine accurately the mass that has been formed. Okay, so CO2 is very similar. It'll absorb onto the mass of another compound, in this case the mineral ascarite, which is composed of magnesium, bromine, and oxygen atoms, and some water molecules. So you would have to take the difference of those two and then find the mass of CO2. Okay, so let's do an example here. So assume that a 3 milligram sample of aspirin, so that's a very small sample, was analyzed in, say, our combustion apparatus above in the picture. Okay? So, aspirin is known to contain 3 elements: carbon, hydrogen, and oxygen. The results of the analysis found that we had 6.60 mg of CO2 and 1.20 mg of hydrogen. Were formed by burning the aspirin. So what percent of aspirin by mass is carbon and hydrogen? Okay, so we have carbon dioxide and water, but we need to figure out, which one, how much carbon and how much hydrogen is in the compound. So first, we're going to convert both CO2 and water into moles of these compounds. Okay, so let's just start by going over molar conversions. Okay, so we have 6.60 mg of carbon dioxide. First, let's convert this to grams. So you don't have to convert to grams, but I figure it's easier to work with if you just convert to grams because molar masses are on a gram scale. So I just think that's a little bit easier to work with. All right, so we know that for every 1,000 milligrams, we have 1 gram. So the metric system conversions, you absolutely need to know. You need to have them memorized, or you just have to know those. For other SI measurements. So the metric system, so non-metric system unit conversions like inches to centimeters, pounds to grams, etc. Those you don't need to memorize. Okay, we will provide those. I will provide those. So it's equal to 1 gram. Okay, so in this case we get 0.00660 grams of CO2. So when you're multiplying by a factor of 1,000 or dividing by a factor of 1,000, you have to just move the decimal place 3 places to the left if you're dividing, and then 3 places to the right if you're multiplying. And that makes sense, right? Because you're multiplying, numbers getting bigger, so your numbers should increase. And then if you divide, your numbers are decreasing, so you should move to the left to make your number smaller. Okay, so 0.00660 grams carbon dioxide. And then now let's convert milligrams of water. 2 grams. So the same conversion here, 1 gram over 1,000 milligrams. And that will give us 0.00120 grams of water. And another way to kind of figure out how you should set up your conversion factor is, do your units cancel? So just treat milligrams as the unit X, right? So if I divide X by 1,000 milligrams, or X, those will cancel out. So if I flip the sign, I'll have times 1,000 milligrams or times 1,000 X. And we know X times X gives us X squared, but we don't want X, right? We want Y, or grams. So we need to put grams on the top of the fraction and milligrams on the bottom of the fraction. So we could just go over there and just say, oh yeah, the units do cancel. And then what we're left with is grams carbon dioxide, grams water. Okay? All right, so after we converted it to grams, we're going to convert each of them to moles. Okay? So let's start with carbon dioxide. So we have 0.00660 grams CO2. Okay? Now we know that for so we have to find the molar mass of CO2. So the molar mass we have carbon is 12.01 grams. For oxygen, it's about 16.00 grams. So on the periodic table, you should at least use 2 decimal places. You can use more, but you shouldn't use any less than 2 decimal places. For all my chemical calculations, I'll only be using 2 decimal places. So on the exam or on a quiz, you probably just want to use at least 2 decimal places. Okay? So if we do this, we get, if we add these together, we have times 2 here, and then 12. This will give us a total of 44.01. So we're going to do that, 44.01 grams. Remember, grams should go on the bottom of the fraction because we're going to convert to moles. And this will be mole CO2. Okay, so if we do that calculation here, let's do it very quickly. 0.00660 divided by 44.01. We get 0.0001499. So we can round that to 0.0001500. 1500. Yeah. So 1500. So I keep an extra sig fig just in case there's some rounding error at the end. So I encourage you, when you do these calculations, if you have intermediate calculations, always keep a few extra digits after the decimal point that you should round. And in this case, it should be 3 sig figs. So I'm going to underline where I should have round. It'll be right here. But I kept I kept an extra digit just to ensure that my calculation is not there's no error in the calculation by rounding prematurely. Okay, so there we go. I keep at least an extra digit just for rounding purposes. Okay, so that's for carbon dioxide. Now we have water, so 0.00120 grams of water. Okay, for this example, water, we know hydrogen is 1.0. Hydrogen is about 1.01 grams for hydrogen. So we do times 2 for hydrogen here. And then oxygen is, again, 16. So 16 grams for oxygen. Okay? And so if we sum this up, we get about 18.01. Oh, sorry, 18.02, grams. So we get per mole of water here, we get 18.02 grams. 18.02 grams of water. Okay, so those grams of water will cancel out here. So we get 1.1. Yeah, 2. Yeah, okay. So we get, so we're going to divide 0.00120 divided by 18.02, and we get 0.00. So we're going to have a really small number here, 0000. So 4 zeros. 6659. So we're going to say 6659. Okay, so for 6659, it's going to be 3 sig figs, right? So I'm going to underline where I would have rounded, and it'll be under where the 5 is. That's where I would have cut off my number in accordance with significant figure rules. But I'm going to keep an extra digit just so I'm not rounding prematurely. Okay. Okay. So if we do that, now we're going to convert moles of each compound to moles of carbon and hydrogen atoms. Okay. So for CO2, we know that for CO2, we're going to have, so I'm going to write under here moles of CO2, moles of water. So we know on step 3, right, we're going to convert these moles of each compound to moles of actual atoms. So let's take a look here. So we have 0.0001500 mole of CO2. And then for every molecule of CO2, we know that we're going to have 1 carbon atom per molecule of CO2, right? Because there's one carbon atom in the formula. So we're going to say for every mole of carbon dioxide, we have 1 mole CO2. We're going to have 1 mole carbon. Based on the chemical formula, there's 1 carbon atom, so we're going to have a total of 1 mole per 1 mole of CO2. Okay, and that gives us 0.0001500 mole carbon. Okay? So now we're just talking about atoms, right? So we're not talking about diatomic elements like, the hydrogen molecule or the oxygen molecule. We're not talking about that. We're just talking about composition-wise, the atoms itself. So in this case, when we say oxygen or hydrogen, we're not meaning the molecule, because in the sample, hydrogen is not represented as H2. It's just represented as different hydrogen atoms bonded to different, say carbon atoms, right? So it's not going to be the H2 molecule or O2 molecule. It's going to be the H atom or the oxygen atom. Okay. So that's for carbon. Let's do now for hydrogen. So we have 0.0000. So feel free to represent this in scientific notation. I have not done that for this example, but feel free to do that so you're not making mistakes when writing out all the zeros. So we have H2O. Okay. All right, so here we have, for every 1 mole of water, so remember, put the moles of what you started with on the bottom of the fraction, because we're trying to convert to something else. We're not going to, are we going to have 1 mole of water, hydrogen atoms, or 2 moles? Well, if we look at the formula for water, it says H2O, so that means there's 2 atoms of hydrogen. So we're going to have 2 moles of hydrogen atoms. So 2 moles of hydrogen. Okay, so we're going to multiply this number by 2. So we're going to multiply this number by 2. We get 0. Okay, so we get 0.0000000 1333318. So I'm just going to copy all the digits here, but I'm going to underline where I would have rounded, is at the 3 point, and for carbon at the 0. Hydrogen. So feel free to, you can't, in these intermediate calculations, you are free to, you are allowed to copy as many digits as you want, but in your final answer, you must not list all the digits. That will be wrong. So each instance students do that, I will have to take points off. And what I'll say by my comment there, I'll say sig figs, watch for sig figs. Okay, so now we have moles of carbon and moles of hydrogen. Now let's convert these to moles of carbon, from moles of carbon and hydrogen to grams. Okay, so for carbon, we're going to say we have 0.0001500 moles of carbon, and we know that the molar mass, so the molar mass of carbon, so when you're doing these things, have your periodic tables out with you. You'll be able to use the periodic table on the exam. So for every 1 mole of carbon, there's about 12.01 grams of carbon. So we're going to multiply that by our moles here, and then we will get a number that represents the total grams of carbon in our sample. Okay? 0.0001500 times 12.01, and we get 0.0018015 grams of carbon. So let's underline where we would round in sig fig. All right, now let's do hydrogen. So 0.000133318 mole of hydrogen times, we know that for 1 mole of hydrogen, we have 1.01 grams of hydrogen. So essentially, when we do this calculation, it's just going to be the number itself, but just a little bit higher, or just maybe a little bit higher because it's multiplying by 1 times 1.01. So we get 0.0001345 grams of hydrogen. So let's just keep this digit to the dirt sig fig, and then we'll know where to round at the end. Okay. So that's our mass there for carbon and hydrogen. Okay. Alright, so in the next video, we will go over now in the next step to calculate the percentage of each element. So I'll see you then.